In this series of videos, we're going to discuss the viscous flow in pipes. Now, pipes or pipe-like objects are found in many engineered systems, such as HVAC systems and pipelines, but as well as in nature, such as blood arteries. Now, the definition of a pipe is a closed conduit through which fluid flows. Now, more specifically, a pipe has a round cross-section, whereas a duct, which we would find in an HVAC system, which stands for heating, ventilation, and air conditioning, would have a non-circular cross-section. For our analysis in this chapter, we will need to apply many concepts from previous topics, such as control volume analysis, Bernoulli's equation, dimensional analysis, and some others as well. What we seek to answer in our study of viscous flow in pipes can be the following. We might want to ask, what is the pressure loss along a pipe section? Or let's say, if I want to move a fluid from one point to another, given certain parameters, how much energy should be added to my system? And that form of energy could be, let's say, a pump that we need to size for a certain piping system. And then finally, an important thing is that we will no longer make the inviscid assumption. And recall that an inviscid flow is an ideal flow or an idealized flow where we neglect the effect of viscosity. So naturally, in a chapter that discusses the viscous flow in pipes, we can no longer neglect viscosity. So let's touch on a few definitions and general characteristics of pipe flows. So let's consider we have a pipe, and here we have some velocity profile. Okay, so, and we're not going to make any restrictions on what that velocity profile looks like and whether even we have a laminar or turbulent flow in this top image here. So we have some velocity profile, and notice that our velocities go to 0 at the walls due to the no-slip condition. We can also define an average velocity. And this average velocity will of course depend on the velocity profile and the flow regime in which we find ourselves. Now consider that we place a velocity probe somewhere in our pipe. Okay. Now, if we were to look at a time series of the velocity probe, we would see two very different looking time series depending on whether our flow is turbulent or laminar. So for a laminar flow, we would see that the velocity at point A would be constant. For a turbulent flow, on the other hand, we will see a lot of oscillatory motion for the velocity signal. We can still define an average velocity for that point for a turbulent flow. So this is what we would expect if we were to look at a time series of a turbulent flow or a laminar flow at a given point. So as stated here, for a laminar flow, the particles will follow straight lines. For the turbulent case, the mean velocity at that point is unchanging, but the instantaneous velocity can definitely change between different instants in time. And this is what we're seeing over here. So we have a very noisy signal with a mean in green that is not changing with time. And in our study of viscous flows in pipes, we are going to assume that the flow is steady. meaning that the mean properties at a given point are not changing with time. Let's discuss the onset of turbulence. So the onset of turbulence was first mathematically characterized by Osborne Reynolds, who conducted a classic experiment which demonstrated that the onset of turbulence is dependent on a certain number, which is now known as the Reynolds number. The Reynolds number takes the form of rho v d over mu, where d is a length scale, which in this case is the pipe diameter, if we are looking at viscous flows in pipes. Keep in mind, however, that we can define a Reynolds number for many things other than just pipe flows. We can define a Reynolds number for an airfoil, where our length scale will not be a diameter, but it could be, let's say, the chord length of the airfoil. We can define a Reynolds number for a flat plate, and so on. Now, recall just from our previous discussion that the velocity, it might have a certain velocity profile. So the velocity is changing in the radial direction. So which velocity are we using in the Reynolds number? In this case, what we do is that we use the average velocity. So we define this v bar as the average velocity in the pipe. And again, d is our pipe diameter, mu is our dynamic viscosity, and rho is the density. And empirically, it's been estimated that for a Reynolds number of less than 2100, we have a laminar flow. For a Reynolds number greater or equal to 4000, we have a turbulent flow. And for Reynolds numbers between the two, we have what is called transitional flow. Now, transitional flow is where we might see some hints of a turbulent flow, but the flow is not fully turbulent. Okay? Now, recall what the Reynolds number is telling us. The Reynolds number, and we looked at this in dimensional analysis, the Reynolds number gives us a sense of the relative importance of the inertial effects relative to the viscous effects. Okay, so a high Reynolds number flow has the inertial effects being the dominant ones in the flow. So we can think of our inertial effects as the momentum of the fluid. A low Reynolds number flow, on the other hand, has viscous effects which are more dominant. In turbulent flows, instabilities cause small disturbances to an otherwise steady flow, and these can grow into observable fluctuations, as we've shown in this image over here. On the other hand, for a laminar flow, the viscosity dampens these small disturbances and the flow remains steady. And as we've mentioned from this dimensional analysis, as the Reynolds number increases, the relative significance of the viscosity decreases. Next, we turn our attention to the concepts of the entrance region and fully developed flow. So consider this image over here. We see we have a filled tank, which is allowing a fluid to enter the pipe on the right. So the entrance region is the region near where the fluid enters the pipe. As we can see, right at the entrance of the pipe, the flow is approximately uniform at the inlet. So we see that our velocity vectors are more or less constant across the diameter. But as the flow moves in the axial direction, the flow begins to, in a way, feel the effect of the walls through the effect of viscosity. And how this manifests itself is through the growth of a boundary layer. So the boundary layer, as we can see here, is growing and growing in the direction of the flow. So once the fluid reaches the end of this entrance region, the velocity profile remains constant. And I've tried to draw it as best I can, but of course my drawing is not fantastic. So this profile here, regardless of whether it is a turbulent velocity profile or a linear laminar velocity profile, this velocity profile remains constant in the x direction in what we call the fully developed region. So what we can say is that in the entrance region, the velocity profile is a function of both the radial position and the axial position. However, on the other hand, for fully developed flow, where the velocity profile is no longer changing in the axial direction, the velocity is only a function of radial position. So let's look a bit more closely at the differences between the entrance region for a laminar flow and a turbulent flow. So in a laminar flow, the changes in the velocity profile in the entrance region are dominated by viscous effects. So what we mean by this is, recall I briefly mentioned that the flow begins to feel the effects of the wall through the no-slip condition, and therefore we have the growth of the boundary layer. So if we have a fluid element over here with a shear stress on top over here and a shear stress over here, these two are unbalanced. So what we are getting is a local fluid acceleration. In the fully developed region, there is no acceleration of fluid particles, and this is why we see an unchanging velocity profile in the axial direction. So, although we do have a shear stress, it is being balanced by the pressure gradient, which we will look at a bit more closely later on. So we would say that we have an axial pressure gradient of the form of dP by dx. So we say that these two effects, that of the shear stress and the pressure gradient, are in balance in the fully developed region. In turbulent flow, changes to the velocity profile are due to both viscosity and mixing. So what we see in turbulent flows is enhanced mixing through a lot of these rotational structures in the flow. And so this change in the velocity profile is due to both of these effects. And again, keep in mind that what we're saying about a change in the velocity profile is a change in the mean velocity profile. Because even in the fully developed region, so if we say that beyond this red line over here, we have a fully developed region, instantaneously at any point, so let's consider this point over here, the velocity could at one point be over here. The next time the velocity could have a slightly lower magnitude, and so on and so forth. Okay, and the average is given by this red line over here. So in the fully developed flow, again, it is the mean velocity profile that is not changing, but instantaneously, we are still seeing these velocity fluctuations at every point. Another thing to note is that turbulent flows have much fuller velocity profiles. Okay, so let's write this down. And again, we will get into this a bit more later on. So turbulent boundary layers are what we call fuller. Okay, so if we have a boundary layer like this, for the turbulent case, the laminar case is much more of a parabolic shape. So as we can see, near the walls, or nearer to the walls rather, this is the turbulent case and this is the laminar case. So nearer to the walls, we have higher velocity fluid particles in the turbulent case. So what we see is that for the turbulent case, the velocity profile, if we call this, the velocity gradient at the wall for a turbulent flow is greater than the velocity gradient at the wall for a laminar flow. Okay, and this would of course be if we define this as, let's say, our y, and this is our velocity profile, v of r. Now, entrance lengths have been determined for different types of flows. So the entrance length, which we call LE, for a laminar flow takes this form over here. So the entrance length divided by the pipe diameter is equal to 0.06 multiplied by the Reynolds number. On the other hand, for a turbulent flow, the entrance length is equal to 4.4 multiplied by the Reynolds number to the 1 over 6. And these are empirically found relationships. Okay, so in this video, we've introduced the topic of viscous flow in pipes, and we've motivated the topics with the types of questions we might ask. We've looked at some of the general characteristics of laminar and turbulent flows, and we've introduced the concept of the entrance length and that of fully developed flow.